Yes, hi everyone. So I'm on camera today. So we will discuss some topics from matrix and we will try some questions from that. So kind of book reading and some questions there and you have to try them. I just explain the method first. Okay, so let's go on screen sharing. Let me see where is, okay. Is that, okay. Is the screen visible, everyone? All right. Okay, let's go to this book. I hope the screen is visible. So we will start from this time we will study like matrices and some questions over that. So what do you mean by an algebraic equations? Like system of algebraic equations is like having kind of the first equation, second equation, and up to n equations, and you have n equations and n coefficients in every equation. So here x1 and x2 and up to xn are your variables and their coefficients are a11, a12 and up to a1n. Similarly for other types. And b1, b2, bn are the constitute the non-homogeneous part of the matrix. All right, of the system of equations. So you can convert this system of equations into a matrix if I write here somewhere. It's the previous one. Let me take a new one. Oh, I haven't saved it. I just save it first. I haven't uploaded yet. Okay. All right. So let's write here. So if you have kind of a11 x1 plus something a1n xn equal to b1 and similarly to bn, just that is already written there, then you can always write it. So last entry will be an1 xn, so it will be x1 plus an2 x2 up to ann xn, that is this. So you can always write like this, a11 a12 and a1n. Similarly here an1 an2 ann, and similarly like this. So here is the vector x that you can always write as the tuple in the tuple form. Is this clear, everyone? This is easy stuff. I just go with, I hope it's clear. Okay. So after this, so the one thing that I want to note down is diagonally dominant matrices, like the matrices which are called diagonally dominant. If you say that the absolute value of the entry on the other side of diagonal is greater than equal to the sum of this. So for example, yes, so if I write here, what are diagonally dominant? So if I have 1, 5, 6, 2, 4, 3, and 2, 1, 1. So is this matrix diagonally dominant matrix? Anyone? Is this a diagonally dominant one? I just use my camera for, yes. So here you see 4 is greater than equal to 3 plus 2. Then it means that, so it's not greater than equal to 2, so it's not diagonally not diagonally dominant. So you just check. I just give you some matrices which you have to check for the moment. So if I give you this one 0 minus 1 1 minus 1 minus 2 minus 3 or minus 1 5, here I take it's just minus 2 5 5, and here you take minus 10. So just check whether it is a diagonally dominant or not. Check. Just check it. Yes, everyone, have you tried it? So just check it. So here,
Is
don't be
diagonally
confused.
dominant.
Is it? Yes. Why is that? Because minus 2 mod is just 2, which is greater than or equal to 1 plus 1 minus 1 mod. So it is diagonally dominant. This is very easy. Other question that we want to try is, okay, we want to go with other books. Yes. So one thing I want to mention is that, okay, so if you have, are you able to see my cursor on the screen, everyone? Yes. Okay, so if you have a system of equations, ax equal b, that can be written in this form, then when you can guarantee that x is the solution of the system, right? So it says that the inhomogeneous, so if you look at my cursor, it says that inhomogeneous system has unique solution if and only if the determinant of A is non-zero. That is, determinant A is going to be non-zero, then Ax equal B has unique solution, which is given by x equal A inverse B. All right. And if you have homogeneous system, because B is zero in that case, so you want to get the same like zero solution or a trivial solution in that case. And yes, of course, if the determinant is not zero, because if the determinant then A inverse not does not exist. All right. So you cannot write like this. You cannot invert your A in such a way. All right. Okay. So and then we gonna see like what are the eigenvalues. So is this clear, everyone? What is the solution of a system? Yes, I think so. So if you have ax equal lambda x, then we need to find out what is lambda. So you just take ax minus lambda x equals to 0. Then you have a minus lambda I x is equal to 0. Then you need to solve it. You have to find what is x now. Yes, anyone? How to find this x in this case? I want x to be non-zero. I want x to be non-zero. So if you go back in this book, then you have to have a non-trivial solution x not 0. The determinant of matrix must be 0. So in that case, the determinant must be 0, because if determinant is not 0, then x is 0. But if determinant is 0, then x can be anything, right? So you're gonna just do that determinant a minus lambda equals to 0. So that will give you some kind of characteristic equation. So if you can try something like this, so I give you some matrix 5, 1, 2, 3. Okay, maybe a simple one that would be good. Let me raise this one. So I'm gonna give you a simple matrix minus 1, 1, 1, minus 1. So this is your A. Find lambda such that A minus lambda I x is 0. Can you try that? Everyone, just try this one and let me know what's the answer. So have you tried this? What's the answer of this? Anyone? There we are. Okay. So how do you do that? Just the same thing. Just try to calculate determinant of A minus lambda I equals to 0. Um, am I doing? Yes. Okay. And you just try to calculate minus 1 minus lambda 1, 1 minus 1 minus lambda, determinant is 0. So it's just 1 plus lambda square minus 1. And this is just 1 plus lambda square plus 2 lambda minus 1 is 0. Lambda plus 2 is 0. Lambda is 0 or lambda is minus 2. Is this clear? So if you notice one thing from here is that if you sum these lambda 1, lambda 2 together, then lambda 1 plus lambda 2 is minus 2, which is just the sum of the diagonal elements here. So if I do that, so it's just also -2, which is called the trace of A. And similarly, you have determinant of A. Determinant is just the 0 in this case. So here is also determinant is 0. So if you multiply lambda 1 times lambda 2, that's determinant. I hope it's clear to everyone. Yes. Okay, so if it is, let's go to another question. Okay, so what are the methods to solve the system of equations is just by directly you can solve it. So if you have system Ax equal B and A is diagonal matrix, then it's very easy. The solution is just by hand. If A is lower triangular matrix, you can just easily solve it using, so you just find out in the from the first equation, you find out what is your x1. You substitute x1 into your second equation, find out x2. You substitute x1, x2, you find out x3, and similarly go on with the same procedure until you end up finding xn. And you have the same procedure for when A is an upper triangular matrix. I hope everyone knows what is lower triangular and upper triangular matrix. Okay, so we are not gonna do Kramer's rule, that is already done in your, I'm not going to do that. So Gauss elimination, what's that? Okay, so if you have a system of equations, like 3 equations or so, then you can find out the solution using Gauss elimination method. It's kind of elimination. So what is that? What is the difference in this case? Let's see first. So in the first stage of elimination, you multiply the first row by this A21 by A11 and A31 by A11 and subtract from the second and third rows to get this. So what is they are drawing is, yes, so they are subtracting these two entries. They are kind of eliminating these two coefficients, and then they are eliminating these two coefficients and then keeping the thing simple. So if I go with the procedure again, so if you have kind of, so what is Gauss elimination? What does it happen in this? So if you have a matrix kind of 3, 5, 1 or 4, 4, 2, 1 or 3, 5, 4, and you have a big vector x equals to something something 1, 2, 3, whatever. So how do you find out x in this case? X is your kind of A, B, and C. Okay. So you just do row elimination. So here you try to eliminate this entry and this entry using this precious entry on the top row 3. So just eliminate that. So what are the operations? Suppose it is R2 and R3. So you just do R2 minus 5 by 3 R1 and R3 minus. So you're going to need these two things. Okay. All right. So if I go to the next page, yes. So what you're gonna get from this is, I just use a smaller text maybe. So what you're gonna get from this is 3, 0, 0, okay? And you have 4, and again you have to do the same thing. 2 minus 5 by 3 into 4 here. So if I cut this, there's no procedure to cut it. I just used eraser. Oh, there is. Let me take this one over. No, it's not possible, I think so. No, it doesn't work. All right, so You just apply the similar procedures. So 2 minus 5 by 3 into 4, and 1 minus 5 by 3, 1 minus 1 by 3 into 4, and similarly on this 5 minus 5 by 3 into 3, and 4 minus 5 by 3 into, sorry, 1 by 3 into 3. Is this clear, everyone? And once you get these entries, just eliminate this using the previous thing and the similar thing happens. So ultimately you end up with something like this. D, say A, B, C, D, E, F equals to B1, B2. These are all changed now. So A, B's, what is B1, B2, B3. Okay. Is this clear, everyone? Rakshita, Nasir, is this clear? I think so in
Sir,
your, yes, I think so in your lecture notes it's already done, but I'm just recalling the concepts and have a better understanding. If you have any questions, just let me know. So Gauss elimination is a basic method in which you just terminate, you just remove second and third entries. Yes,
constant matrix 1, 2, 3 is also reduced row operation.
which matrix can you repeat? Let me write.
1, 2, 3,
One,
2, 3, which is also under row operation, right?
this one.
Constant
Oh,
matrix
oh, constant. Okay, let me write.
under
Constant is,
row
wait a second.
1, 2, 3.
Constant is just like 111, you know. Is that?
No, sir. Ax equals b, right?
Okay.
Here b is matrix 1, 2.
Oh, B is just 1, 2, 3, you are saying. Yes.
Yes.
So,
Which is
yeah,
also
so this is a non-homogeneous matrix.
yes, sir.
And this should also go into the same operations as your matrix A. So same thing is going on here as well. So if you apply any matrix operation on A, then same thing on B. Is
Okay,
that
sir.
all right?
Yes, sir.
Okay, I think someone is coming. Great. Okay, so let's move forward again and see some new things. So this method is pretty clear to everyone. So another thing that they do is kind of partial pivoting, in which you try to choose okay, you try to choose the maximum of each row and just replace them and on the diagonal. Did you understand this? So if you go over here, and if 3 is not in, if you've seen this type of, I just use the green color. So in this diagonal, if you see that 3 is lower than 5, so you just interchange these two rows. You make 5 as 3 and 3 as 5, and similarly the things go on. It may prove like more kind of faster things to find a solution that has already been done in this. So here is an example. If you want to try using Gauss elimination method, what is the result you will get? Just give it a go. Just try the Gauss elimination and find out the solution of this system. Just try that for a moment. I just make it big. Example number 3.2. Just try that, everyone. So has everyone tried this? I think so. Let's go to other question, other stuff. Okay, so you have done the similar things over here as well. Just eliminate the coefficient of x2 and x3. Sorry, x1 in the second and third row, and then similarly for the x2 and x3 as well. Similarly, you do this in this. So one problem that you may encounter, just try the example number 3.3 for the time being. Just try 3.3. I just make it big. So yes, so everyone has tried this, I think. So what is the problem you want to face in this type of equations is the problem with the coefficients over here. In the first column, there is coefficient 1, 3, 2. In the second one, 3, 1, and 1, 4, 3. So if you apply the first step of Gauss elimination, so I just use the 100%, then you want to get this kind of thing. x1 plus x2 plus x3 is 6, x3 is 2, minus x2 plus x3 is 1. So if you're gonna, yes, so you cannot proceed as usual in the second step. Did you understand this, by the way? You don't gonna proceed in your second step. So you need to interchange your second and third equations. So you always end up in this. All right, which has the solution this. So you need to interchange the equations and then you get the solution. But you will not go with the usual step of the Gauss elimination process. So the interchange part is new for you and it's a bit modified. So similarly, you can try this one as well. And yes, that's very different. That's the same thing. Okay. Is that clear, everyone? I think so. Um, yes, any doubts on this? If you have any doubts, just ask because in your exam you may find such things. In example 3.3, any problems? Rakshita has no.
Yes, sir.
Okay. Okay. So next method is called as Gauss-Jordan elimination method. So what's new in this? Um, let's try to see. So in this case, if you have some certain kind of a matrix, then you just try to invert it in the same way. Like, um, okay, so you put the matrix A somewhere here, I somewhere here, and then you try to invert it. So you try to make 0, 0 here, and similarly, you do the same operations here, like in Gauss elimination. But the thing is that you need to make 1 on the diagonal. So the difference only lies in making 1 on the diagonal until you make it as identity matrix, and then it's your inverse. So in this type of method, you are trying to reduce this whole matrix to the identity matrix and with the operations on the identity matrix. So it's kind of more time taking, and yes, it needs lots of efforts to do that. So most of the people use Gauss elimination instead of Gauss-Jordan method because you need to find out inverse. But ultimately, it is giving you the exact solution at the end. All right. So I think this method is also clear to you. So next method is LU decomposition method. So if you can decompose your matrix in two ways, A equal LU, where L is something like this, U is upper triangular, L is lower triangular, then you can always find out the solutions based on that. So if you, yes, so the thing is, you write A as LU, which is LUX, which is B, and ux equals z is your another equation, and z lz equal b. So I'm gonna write here. So if you see carefully this one, I just take a new slide. Very tired today. Okay, so if you have a equals to lu, where l is lower triangular matrix and u is your upper triangular matrix, then you write, if you have ax equals to b, that implies lux is equal to b, that implies lz equals to b, and ux is equal to z. Okay, so lz equals to b and your ux is z, so you're gonna solve first for ux equals z. So solve ux equals z. um okay, I think z is not provided, so first, wait, I just use the eraser. Okay, where is that pen? So you first find Lz equals to B, find Z. And once you have Z, then find X. Find X from X equals to Z. I think this is very clear. So if you want to try some questions on that, so here is one. So use decomposition method to solve this system. So just try and find out X and X to X. I will ask what are these values. All right. Yes, have you tried this one? Everyone, what's the answer of this? Rakshita, S, Raswit and Naseem, what's the answer of this? Have you tried it? Okay, if you have not, just go by the same procedure. So you write A matrix as something kind of lower triangular. This one is upper triangular with one of the diagonal entries to make it more simpler. So just write one of the diagonal entries or either any of them for either for the lower triangular or upper triangular. And just try to find out what is the values of L11, L21 and these values from A using A. So once you have L, U, then you can find out Z and you can find out X. That's all done. So it's simple case. I don't think so it's so difficult. Any problems in this you can ask. All right. And I go to the next method, which is called as Cholesky method. So this method is also known as the square root method. If the coefficient matrix A is a matrix and positive definite, then the matrix A can be decomposed as kind of L transpose, where L is your lower triangular matrix, or A can be written as U times U transpose, where U is your upper triangular matrix. Okay, so similar procedure going on in this way, and where in the past method you have written A equal LU, instead of U you just have L transpose, and here as U transpose, so it's almost same kind of stuff, and then you get your answers similarly. So if you want to try this, you can always use Cholesky method, free to use. All right. So I'm not going to go in this method more details. So I'm going with some kind of another method that, yes, so I'm going to vector norms. I think you have seen them before. So the first norm is, so these are the some norm properties. The first norm is your absolute norm, Albert norm, where you just sum the absolute values of xi's, right? And the Euclidean norm and the maximum norm for a vector. So for a matrix, we are going to calculate what do you mean by Frobenius norm or Euclidean norm. You just find the absolute values of all the coefficients, square them and sum them over all your entries and then square root. Similarly, maximum norm, you find out maximum absolute row sum, maximum absolute column sum, and so on. Spectral norm, I think this is something that I should know, I should say about, but I don't think so here. Okay, all right. So you just try to find out one thing. If I say you have a matrix here, suppose 1, 1, 1, 1, what is the Frobenius norm? Or you say it as, wait a second, or you say it as FA. Yes, I think it is 2 norm. So it is also called as 2 norm. So just try to calculate what is 2 norm of this matrix. Just try to find it. It's becoming colder. Yes, just try to Yes, what's the answer of this one? Can you tell me? So if you go by this, you just need to square every entry and sum, and then square. So a square is just 1. So I just do 1 plus 1 plus 1 plus 1 and then square, which is just 2. So nothing much, okay? Someone is trying to join again. Yes. Okay. All right. So we go with the, so you can easily calculate absolute row sum, column sum and all. So what is Hilbert norm or spectral norm? Hilbert norm is just, oh, I've used the another notation, I think so. Okay. So Hilbert norm is the square root of lambda, where rho is your, so what is this row basically? Maximum eigenvalue of A star K, I think so. Okay, yes. Why everyone is coming, leaving? All right. Okay. So in most of the questions, you will see that they will try to find out what is called as condition number, and it is just norm A2 times norm A inverse 2, which is square root of lambda by mu, where lambda and mu are the largest and smallest eigenvalues in modulus of A star. So if you have to find out the condition number of a matrix, just try to find out the norm 2. So it's, so what I've discussed here is not norm 2 actually, but it's a different one. So I just write here norm. So it's not norm 2. Norm A is, so if I gonna define the spectral norm, then it is just norm A2, which is just, oh, what is that? This is just square root of rho of A star. Right? I think so. Okay, so norm A2 is defined as the, we go, square root of lambda, where lambda is rho of A star A, absolute eigenvalue of A star A. So defined as, so if you go here, norm A times norm A inverse. Okay, so you have to find out, maybe try to find out condition number, find the condition number of the system. So try example number 3.9 and find the condition number of this system. Okay, just give it a go. So have you tried this, everyone? Where we are. So you just try to calculate A star A, which is just A transpose A, and which is just, you know how to calculate, how to multiply two matrices. Eigenvalues, you know how to calculate eigenvalues as well, and you try to calculate, okay, so lambda 1 and lambda 2, okay. The condition number is this one. Okay, so if you have, yes, so lambda star and v star largest and smallest eigenvalues in modulus of A. So just find the largest and the smallest one and then calculate the square root of that. That's it. So your condition number for 2 by 2 system. And similarly also for condition number is lambda and mu are largest smallest because A inverse. What are the A inverse eigenvalues? You know that. This is just the inverse of your that one. Yes. Is this clear, everyone? Any doubts you can ask now. If you have any problems, any doubts, just ask.
Sir,
That's all I
can you
want. Yes.
last previous problems?
Yes. Yes. Which one is this one?
A star A. Yes, sir.
A star. Yes.
Once explain, sir.
Oh, what is A star is? Okay. Let me write here. So A star is just A transpose if A has all real entries. Okay. Otherwise, it's A transpose conjugate if A has complex entries. Is this clear? Rakshita, is
Yes,
this clear?
sir.
Conjugate, you mean? You know what is conjugate? I think so, you know. That's A plus IB, and if you conjugate it, it will be A minus IB, okay?
Yes, sir.
Okay. Any other doubts? Others? Any other doubts you have? I will be closing this session in another 5 minutes. If you have any doubts, you can ask.